Section 13.2, line integrals, video 14. I almost forgot a very important thing to conclude with about comparing the line integrals of vector fields versus line integrals over scalar fields. Make sure I just phrase that last part correctly. Yes. What do I mean by a scalar field? Well, it's like a vector field except with scalars. A vector field says, give me a point and I'll give you back a vector. A scalar field says, give me a point and I'll give you back a scalar. In other words, a scalar field is just what you would think is a regular function. Put some numbers in, get one number out. A single number is a scalar because it has magnitude but not direction, whereas a vector field would give you back both something with magnitude and direction. All right, so let's go for the generic setup. Suppose we have a vector field in 3 dimensions, so some vector function f of x, y, z, where the component function for I is called p, so p of x, y, z returns a number, not a vector. The component function for j is q of x, y, z, and the component function for k, is r of x, y, z. So these would be called scalar fields. They return scalars. Collectively set up like this, they are a vector field. And curve C is parameterized by the position function vector r of t equals x of t times vector I plus y of t times vector j plus z of t times vector k. So in other words, x of t, y of t, and z of t are the scalar functions that give the components for the position vector at some value of t, and as usual, t is ranging from a to b. So how can we set this up? How can we set up the line integral of this vector field dr? Well, let's think about what these things mean. We'll go ahead and go from a to b because we're about to make the transition to just t's. This function, evaluated at that, is the vector pqr. Again, I'm shifting to the pointy parentheses notation for brevity, and I'm leaving out the x, y's, and z's as the inputs with the assumption that we already know that they are the inputs. Dot, the derivative of the position function. Again, using the pointy parentheses notation, the derivative of the position function is just x prime t, y prime of t, z prime of t, dt. Well, to form a dot product, you just take the sum of the products of the corresponding components. So it would be the integral of p, we'll say p of, do we need to get more explicit here? Yes, p has 3 inputs, x, y, and z, but each of those are functions of t. So p of xt, comma yt, comma zt, times x prime t dt plus q of x of t, comma y of t, comma z of t times y prime of t dt plus r of x of t, comma y of t, comma z of t times z prime of t dt. So what's the big hoopla here besides having a huge mess? Well, we have 3 line integrals with respect to x, y, and z. Remember that a line integral with respect to x has just the derivative of the x function as opposed to the derivative of the whole arc length function. And the same thing with y and the same thing with z. So we could write this a lot more compactly as saying the integral from a to b of p dx, yes, plus q dy plus r dz. And suddenly, evaluating this line integral becomes easy. We just integrate the p function, once we've changed x, y, and z in terms of their parameters, with respect to x, so we would have to multiply this times the derivative of the x function dt. Yeah, recall that this is dx, this is dy, and this is dz. So you still have to recall those things when you write this notation. But you just integrate your I component function, once you change all the x, y's, and z's to t's, times the derivative of the x component function, integrate, and then integrate the j component function times the derivative of the the j component function in the position vector with respect to t, and integrate the the k component function here, once you've changed x, y, and z to t's, times the derivative of the k component function from the position vector with respect to t. So it's a little more compact way of writing, hey, we can do three separate integrals. This times the derivative of this, everything in terms of t. This times the derivative of this, everything in terms of t. This times the derivative of this, everything in terms of t. So we can bypass the dot product setup and just get right down to here. And of course, if this were in 2 dimensions, then we just wouldn't have the rdz at the end. So it's another way, it's a fourth way of representing a line integral, but as a sum of line integrals of scalar fields instead of vector fields. Because again, each of these functions, p, q, and r, are called scalar functions because their outputs are scalars, aka real numbers, as opposed to vectors. All right, so I just wanted to wrap that up, and if you want to see the summary of it again, I recommend looking on page 770. I hope these videos have been helpful, and I hope to find some time to do videos for 13.4, the fundamental theorem for line integrals, and for, I'm sorry, that's 13.3, and 13.4, Green's theorem. I would love to get to 13.5, 13.6, and finally 13.7, which is surface integrals, and then finally 13.8, which is Stokes' theorem. But we'll see how far I can push these videos for Mr. Walker.